Cool. Yeah, so my name is James Grants. I'm the Customer Success Manager here at IMeasureU. And I'm excited to be presenting this webinar with Nick Gallimore because this is a joint IMeasureU Vicon webinar, which we haven't done before. So just a little bit of housekeeping before we get started. You will be able to ask questions, so there's a Q&A portion on the bottom of your screen. As you have questions throughout the webinar, put them there, and then at the end of the webinar, we'll open it up and we'll pick some questions to have Nick or myself answer. It's being recorded, so if you have to leave early, you will be sent the recording after it's done processing, which will probably be sometime around tomorrow. And at the end, we'll just direct you to the IMeasureU homepage so you can kind of explore kind of the things that we're talking about. So let me introduce my co-host, Nick Gallimore, and then I have a few slides, and then he'll do the bulk of the presentation. But Nick is a customer support engineer for Vicon Motion Systems, specializing in the life science and engineering fields. Nick's main role is to help customers achieve the maximum potential from their Vicon system and software, as well as completing system installations and running software training courses. Before joining Vicon, Nick completed his degree in sports science and physics and master's in sports biomechanics at Loughborough University. So I know we have kind of a mixed group here, where usually our webinars are made up of either just IMeasureU customers or just Vicon customers, but I know we kind of have a spattering of both. So I thought I'd just take you through a little bit of the ecosystem with our Blue Trident sensors. So basically, the Blue Trident sensor opens up a few different options for you in terms of recording. So what I'll be taking you through is IMU Step. Just really quickly, that is our lower limb load monitoring solution. And then Nick will touch on the IMeasureU and Vicon side of it. So what IMeasureU Step is, that is our lower limb load monitoring solution. So unlike IMeasureU, the sensors here are in a set position, and that's going to be on the ankle, on both ankles. And the software is set up so that we're detecting steps and we are detecting different measures that we put into already built metrics. So basically it's a plug and play solution. You put the sensors onto your athletes or patients. We have some customers of the military as well. And then once you've done the recording, you'll upload those to the cloud and we'll actually build out some metrics for you automatically. So you still can get the raw data, but it's kind of the out of the box solution where you get those metrics. So it's pretty similar to IMeasureU and how it's set up. Everything's kind of run through the iOS app. The sensors are what's recording, obviously. Again, those are placed on the ankles, and since we have that, we kind of know where we'll be recording. And so once we upload it to the cloud, we'll process that data and provide you with some different metrics there. So the dashboard is going to be our cloud portion. That's going to be where those metrics are stored. Probably the biggest two that we use for both load monitoring and rehab would be impact load, and actually impact asymmetry is releasing today. So if you are an IMU Step customer, you'll be getting that sometime this afternoon. But basically these allow us to figure out how much the subject is doing and also what was the quality of that movement that they were doing. So once you do the measurement, you don't really have to fiddle around with that raw data. It's all going to come in here, and we'll be able to kind of detect any asymmetries, show you how they're loading, compare it to other days before that. We also will do kind of the basic step count and another metric called bone stimulus, which is really helpful if you're doing bone rehabilitation. So that's just a little bit of background on STEP if you don't know what that is. If you have any questions about that, feel free to contact me after. But I'm going to hand it over to Nick, and he's going to take us through the other two parts of this ecosystem, which will be IMeasureU and Nexus.
Cool. Great. Thank you, James, for the introduction. I'm just sharing my screen. So hopefully you can all see that now. Make that a presentation as well.
Yep, we're good.
Excellent. Great. So welcome to everyone who's joining us today. So thank you for taking part in today's webinar. As you can see, the main topic of today is how we integrate inertial sensors into our Vicon ecosystem, as well as using the Blue Trident sensors as a standalone product. So just to echo what James has said there, this is a joint webinar with Vicon and IMeasureU. So I'm expecting that there'll be some customers or some of you joining who are purely IMeasureU customers. Some of you will be just Vicon customers yet to explore IMU data collection. And hopefully as well, there will be many of you that have both types of equipment available. Excuse me. So hopefully today we go through a wide enough range of topics that everyone taking part will have something to take away. So I'll start with an introduction into what IMUs are. Before we move on how we integrate the Blue Tridents into Nexus, followed by using them as a standalone product through the CaptureU app. And then we'll look at some of the applications of IMUs in motion capture and sports science. So in this introduction, I'll try and answer the following questions. What is an IMU? Where can we find IMUs? How can we use them in sports, in biomechanics and motion capture? And why is there a need to combine IMU and optical data together? So firstly, what is an IMU? IMU just stands for Inertial Measurement Units, and they are electronic devices made up by the combination of 2 or more sensors, which are usually accelerometers, gyroscopes, and magnetometers. They measure the forces and angular rate of an object, and with sensor fusion, the orientation of that object can also be measured. Here we have a picture of a very early IMU. This is one that was used on the Apollo spacecraft in the 1960s and 70s. And just to give you an idea of the size of this IMU, the innermost cube or central part is a 6-inch cube. This was part of the spacecraft's primary guidance, navigation, control system, and allowed the astronauts to continue at their missions when they were unable to communicate with Earth. As time went on, the technology was developed, and these questions got a lot smaller, as you can see here, meaning that IMUs could be used more widely throughout the development of new technologies. Some examples of where we can find IMUs today include planes, drones, and many other types of aircraft that are both manned and unmanned. They are used in head-mounted displays, which are used for virtual reality. They're widely used in robotics research. And of course, you can find them in your mobile devices and smartwatches. They help keep your screen correctly rotated. They help orientate you when you're using maps. And they also count your steps as well. So as you can see, there are many applications of IMUs. So where do these IMUs fit into sports science, biomechanics, and motion capture? Well, the answer comes in the form of wearable technology. And here we have our Blue Trident IMU being worn by an athlete out on a basketball court. The data collected from this sensor will be able to provide coaches and the athlete himself with an insight into performance that had not previously been possible. This is because traditionally optical motion capture systems and biomechanics research are restricted to a lab space. These wearable IMUs gives you the ability to take motion capture out into the field, whether it be on a running track, cricket pitch, or basketball court, just to name a few. The use of IMUs in sports it spans across almost all sports. So let's take a look at some of the applications of IMUs in sports biomechanics with a video that was filmed last year at the University of Western Australia.
My name is Jacqueline Alderson. I'm an Associate Professor here at the University of Western Australia in Sports Biomechanics and Clinical Biomechanics. It's been a pleasure to have Vicon and the IMeasureU team here this week, helping us with our field-based testing, predominantly in cricket, but testing some sports applications using their next generation inertial sensors, and also using their optical motion capture system, their outdoor system. We're looking at using the next generation sensors for a range of sports applications here at UWA, ranging from illegal action testing in cricket to injury prevention for junior bowlers in terms of looking at things like shoulder and trunk counter rotation, And also we were looking at it in terms of whether it had capacity to work for cricket bowling and soccer kicking and a range of other applications. We've been really happy with what we're seeing here today, and look forward to a long and prosperous relationship with the Vicon and IMeasureU team.
So there we saw how the sensors attached to the athletes measured the segment accelerations. This can be used as a measure of performance or even monitor an athlete's return to play. And we also heard how current research studies are investigating the use of IMUs in illegal action testing in cricket and injury prevention for junior bowlers by measuring shoulder and trunk counter-rotation. In addition to just sports biomechanics, IMU data is also being used in military applications for load monitoring at the ankle, as well as in orthopedics and rehabilitation. One of the things we saw in the video was the combination of the marker-based optical motion capture and the inertial sensors. And to do this, we integrate the Blue Tridents as part of our Vicon ecosystem. This gives you synchronized data capture of the 3D markers and your inertial data. We will want to do this for two main reasons. Firstly, to validate any new IMU model against Vicon's gold standard optical data. And secondly, using the optical and inertial data together in the development of new models and research. So that brings us on to section 2 of the webinar, which is the Blue Trident Nexus integration. In this section, I'll take you through how we connect the sensors to our motion capture systems, how we can calibrate the sensors in order to use the global angle outputs, transferring data from the sensors to the PC, and how we can view and export the IMU data. Before you start, just make sure you are running the latest version of Nexus available to download, which is currently 2.11. And secondly, since the sensors connect over Bluetooth, you will also need a supported Bluetooth dongle, which needs to be plugged into the Capture PC. So I have a screen recording here, just taking us through that process of connecting the sensors. So firstly, you open up Nexus and allow all your cameras to connect as usual. And once everything in the system tree is green, you can go to your devices node where you can right click and select modify whitelist.
Hey, Nick. We're getting some reports of a bad echo. Can you just mute and unmute your microphone?
Yep, one moment. Just, sorry, because I'm in presentation mode. Okay, how does that sound? Is that a bit better?
Yeah, it always sounded good to me. Jack, does that sound better to you? Yep, that works. Okay, go ahead, Nick.
Thanks. Great, so let's just start that video again. So again, we just open up Nexus and just allow your cameras to connect as you usually would. I think we got to the dialog window before. Let's stop there. Great. So in the dialog window that pops up here, you can see all of your Blue Trident sensors listed that you should expect to see. And then you can go ahead and just select the sensors that you require. So it's always a good idea to make a note of the sensor serial numbers that you'll be using. And you also have the option here just to search for specific sensors, or if you're using all of them, you can highlight them and use the check selected button. So when you click OK, this then brings the sensors into your system tree. And it takes a moment or two just for them to all get picked up by the Bluetooth and to connect. Once they all go green, it means that they are connected and streaming data. There we go. So in a 3D perspective, you can also notice there's a coordinate system displayed for each sensor. And you can also view the live data in the graph view. Now that the sensors are connected, you first need to choose which components of the sensor you wish to use. So in the properties of each sensor, we have an output preset. This allows you to select either individual components, such as just the accelerometer or just the gyroscope, or you can have combinations of each component, or you can just select all outputs. The outputs that you choose will affect the capture rate of the sensor itself, and that's recorded here as the record rate. So this table just takes us through how the capture frequency adjusts based on what components you include. As you can see, when global angles are included in the output frequency, the capture rate is 225 Hertz. When we remove the global angles, this then increases to 1,125 Hertz. And finally, if you're only capturing the high G sensor, then this is recorded at 1,600 Hertz. So it's really important that you know which components you're interested in and just make sure you're selecting the ones that are valid for your research. Also in the properties of each sensor, we have a stream rate that can be set at either 30, 50 or 100 Hertz. This is the frequency that you can view in real time, and it can be adjusted to improve your real-time stream depending on the components selected and the number of sensors connected. So the more sensors that you have connected to the system, reducing this to 30 will improve the real-time feedback. And likewise, if you only have 1 or 2 sensors connected, you can increase this to 100 for a higher preview rate. Nexus can support up to 18 sensors. We also have the option to include a Vicon beacon as part of the system. The beacon produces a radio frequency which hard synchronizes the sensors to the cameras. When a beacon is not present, then a soft sync is achieved via the Bluetooth. So once you've got your sensors connected and streaming the required outputs, we may be ready to capture. Or do we first need to calibrate the sensor? If you are only interested in the raw data from the individual sensor components, such as the accelerometer, the magnetometer, or the gyroscope, then you can just go ahead and start capturing your trials. However, if you're also interested in the global angles, then you must first calibrate the sensor before capturing. This is to ensure that the global angles are stable and to minimize any drift. To do this, we first attach the IMU to the active wand using an IMU alignment clip, like so. You then go and select the sensor that you've just attached to your wand, and then go to the IMU tab, where you will find the alignment section. Under World Alignment, click Start, and you should notice that the active wand is now being tracked. The sensor can be calibrated by waving the wand in a figure of 8 pattern for approximately 10 seconds before clicking Stop. The IMU then needs to be allowed to self-calibrate before you can start capturing, which takes about 10 seconds. This process does 2 things. It calibrates the sensor for calculating global angles by taking into any sort of magnetic interference within your environment. And it also aligns the sensor's global coordinate system with the Vicon global coordinate system. So as you can see here in this video, we've now gone on to start capturing data. After you've captured the required data, you need to download the data off the sensors onto your PC. To do this, first connect your sensors to the PC using the USB adapters. The trials will be visible in the IMeasureU window, and you can transfer the files just by clicking transfer. You may need to repeat this process depending on how many sensors you can connect to the PC simultaneously. You can then open up the trials and view the data in full. You'll also notice that the sensor frequency is reported as per the sensor capture rate and not the stream rate. You'll then be able to export this data using the export Ascii pipeline, which gives you a CSV file. And in this pipeline, you have the option to export either the raw frames or the MX frames. To show you what that means, here we have the data exported using the MX frames option. The data has been upsampled to achieve an integer number of subsamples for each trajectory frame. Or in other words, for every camera frame, we have 3 frames of data. When you use the raw frames, the data will be exported at the rate it was captured onto the sensor. In this case, it would be 225 Hertz. Alternatively to exporting the data as a CSV file, you can use the Nexus SDK to directly import the data into MATLAB or Python. One of the benefits of doing this is you can then create a pipeline and streamline your data processing. So now that we have captured our lab-based data, we can then take the sensors out into the field. In this section, I'll take you through how we capture data using the IMeasureU app, and then how we download the data from the sensors with IMeasureU Desktop. The app can be downloaded onto any iOS device, but we recommend having iOS 13 or above, and also with Bluetooth 5 for best results. There are 4 different capture methods that we can use. So firstly, capturing to the sensor. This will record data directly onto the individual sensors included in the trial. And using this mode, you can have up to 20 sensors with up to 15 axes of data, each component capturing at their maximum frame rate. For example, the high G sensor will capture at 1600 Hertz. You can include a reference video, and the sensors have an unlimited range, meaning you are not restricted to the Bluetooth connection. Next is capture to device, which streams data from the sensors directly to your iPhone or iPad. This can have up to 14 sensors and a maximum of 12 axes, depending on which components you include in your data capture. The sensor frequency is reduced to half the maximum rate, so the high G sensor would be reduced down to 800 Hertz. Reference video is again available, and the range is limited to about 20 meters to maintain the Bluetooth connection. One of the great advantages of this mode is being able to directly acquire data from the device, which skips the need to connect your sensors to the PC. So finally, we have the real-time insight and AR visualization modes, which can stream 2 sensors together and provide you with an overlaid graph on a reference video. You can also use audio feedback when benchmarks are used. And the AR visualization kit uses the Apple Augmented Reality Kit to fit a skeleton to your subject and display 2D joint angles. This mode is useful for coaches and athletes to get immediate feedback in terms of accelerations, angular rates during movement, such as in the cricket ball. So here I've put together a little video just showing you how we can put that into practice and how we can start using the app to capture data.
I'm ready to go for a run. So to start the session, I'll go to my IMeasureU app, click Capture Sensor, and within the new session, I can select New Trial. I'm only really interested in high G data, so I'm just going to disable these.
Sorry.
Done, and make it. Start the capture. This is where you can then select your sensors. When you click Start Capture, the sensors connect to your phone, and we are ready to start the session. So I'm going to go out for my run now.
Dear, I've skipped forward a couple of slides by accident. Let me just go back.
Come to that app. All right, so I'm back from my run, which means I can now stop the data capture. So to do that, just go back onto that app and click Stop Capture. There we go, then the sensors connect back to the phone and end the session there. Okay, so now that I've got the data I captured, it's time for me to take these off, put them into my PC, and download the data. I now have my sensors connected to my computer, and I've opened up IMeasureU Desktop where you can see my trial listed. To preview the data, select Edit and Download. I can crop the data to my region of interest, like so. And I can just simply click Download. This exports the data to a specified location, which can be accessed by clicking the hyperlink available on the trial. Here you can see we have our 2 CSV files exported, one for each sensor containing high G accelerometer data. Okay, so that brings us to section 4 of the webinar, which looks into the techniques and applications. I'm going to carry on with that running data, which was just captured. And I'll just start by showing you how we can compare left and right leg IMU data. I'll then try and answer some commonly asked questions about sync and global angles. And lastly, we have some sporting examples for taekwondo and swimming. So this is what the data looks like when you open up one of those CSV files. The first 2 columns you see here are your Unix timestamp and the trial duration. Then we have our XYZ accelerometer data, which is output in meters per second squared. To interpret the data, I just imported this directly into MATLAB, but you can use any software which you prefer, such as Python or R, or even Microsoft Excel if you are a first-year biomechanics student. The first thing to take that I can show you is just what the raw data looks like. So here I've just plotted the left and right leg on top of each other with the X, Y, Z axes shown in red, green, and blue. We can't take too much away from just looking at this. So the first thing that I went to do was calculate the resultant accelerometer data from both of those. So I've plotted the left and right together, but as you can see, the left leg, which is plotted in blue, is quite well hidden by the right leg data. So I've zoomed in there to make it a little bit more clear, and hopefully now you're starting to see the right leg is clearly showing some much higher impacts than the left leg. Because I'm only really interested in the peaks from the initial impact from foot contact with the ground, I've put a threshold in of 20 G. So that's plotted by that horizontal black line, which you can see there. The next step is to remove all the data that is below this threshold, which will look something like that. We can then average those peaks for both the left and right side, which gives us an overall picture of the impacts from each leg throughout the run. So as you can see, I'm maybe slightly imbalanced here, favoring my right side. We can also look at the number of impacts which are above that threshold of 20 G, and where we can see I'm also having a much higher occurrence on the right side than the left side.
So to sum that process up, I started just by calculating the resultant accelerometer data, removing data that is below a set threshold, and then averaging the peak impacts. This can then be interpreted by coaches and athletes and researchers in various different ways. So moving on to using your sensors with Nexus. We are often asked about the synchronization between the two systems. So there's many ways that you can verify or validate the synchronization of the sensors when they're included in your optical motion capture system. But here's a simple method in which a tracked marker is just being dropped onto an integrated IMU sensor. The top graph here shows the accelerometer data, and the bottom graph shows you the vertical component of the marker. When the marker first comes into contact with the sensor, we should see the initial reaction from the accelerometer. When comparing the outputs together, we can see that the IMU and marker data are perfectly aligned. And that is the sort of the minimum point of the Z component of the marker, where you'd expect the first initial reaction from the sensor to occur. In this example, I included one of our beacons, which, as I mentioned earlier, produces a radio frequency to hard synchronize sensors with the cameras. So this test can be repeated for multiple different setups, including when a beacon is not included as part of your system, and also for varying capture frequencies and the components that you're including in your sensor. We are also often asked, how are the sensors synchronized with each other when using the CaptureU app? At the start of recording a trial, the sensors are synchronized by a radio beacon, which is broadcast from one sensor to the others. And once synchronization is complete, all of the sensors are aligned to within 100 microseconds. A simple test can be carried out to validate the sync by attaching multiple sensors to a rigid object, such as a metal bar, and repeatedly striking the object so that an impact is recorded for each sensor. So as you can see here, that's just what's happening in this video. And we're seeing the two different sensors that we've got in this video. Those peaks are occurring at the same time. If you're only going to export the raw data, then you may sometimes find the two components are not aligned with each other. This is due to the trigger for data capture is essentially staggered as the sensors connect to your iPhone via the Bluetooth. This is also why the sensor is exported with the Unix timestamp. This is just the total number of seconds since 1st of January 1970. And it can be used to align the sensors as part of your models. So alternatively to aligning the sensors yourself, we also have the option to just export the aligned data at a specified rate. And this just does the job for you. And you can see here the impacts from both of those sensors are perfectly in sync. So next we come on to the question of Imu Global Angles. The question is usually, how accurate are they, or how do we validate them? Again, there are many ways that this can be done. So here's just a easy example, which hopefully you'll also be able to do if you are using an optical motion tracking system as well. So an IMU has just been attached to a rigid cluster here, which is being tracked by the cameras. And as you can see, the global coordinate systems have sort of been lined up as best they could. The top graph that you can see here shows the cluster data itself. So we can take this as the object's true rotation. And the bottom graph is showing the global angles that we can get from the sensor itself. Now these graphs just directly compare those two data sets together. And as you can see along the XYZ components, The Imu Global Angles, which are in blue, very closely follow the optical cluster global angles. So a lot more further analysis can be undertaken to determine the accuracy of the IMU angles. But I'm going to be leaving that up to our customers and users to determine just how accurate they actually are. So next up, we have an example of using the sensors for Taekwondo. Here we have Dr. Raul Landeo from ACU Sydney during a demo that we gave to them just over a year ago. So the video demonstrates the CaptureU real-time insight mode, in which you can see the IMU data is overlaid on top of the reference video in real time. Hopefully you can also hear the audio tones that are coming through. So these are produced when the resultant acceleration goes above a set benchmark. This can be used to track the intensity of each kick and provides audible feedback to the athlete. Again, this can be used if returning to sport after injury, and if you don't want to overexert yourself, then you can set a limit. The same principle can then be applied to any sports in which you want to monitor the intensity of a dynamic action. Some other examples include throwing actions such as javelin, baseball pitching, and cricket, and so on. This can be used for football kicking, and even in track and field events such as sprinting or jumping events. The sensors are also waterproof with an IP68 rating. So this means that not only are they suitable for all weathers, but also for use in a swimming pool. So this trial was captured at the Australian Institute of Sports, where we had a single sensor that was attached to the posterior pelvis of the swimmer. So hopefully as the video is being playing along, you can kind of follow along in the graph at which stage of the trial that they're in. We can take a closer look at the data, and we can clearly split the trial up into its distinctive phases. So firstly, we've got the dive start, followed by the first length. This middle part is where we see the tumble turn underwater. And finally, we have the second length there. So looking in a little bit closer, with the dive start, we can see the water entry points in all three axes, as indicated by these peaks. And then we also get these underwater dolphin kicks, which are seen quite clearly in the x-axis. When the swimmer then emerges and begins to swim in freestyle, we can see the left and right strokes in the y-axis. So the positive accelerometer values here indicate a clockwise rotation of the pelvis in the transverse plane. And likewise, the negative values indicate the anti-clockwise rotation. We then come to the underwater tumble turn. When we look at the X component in red, we can see the exact moment that this tumble turn actually occurs. So you can see he's sort of flipping vertically over his own head. This again is followed by these underwater dolphin kicks, and you can also see them a bit more clearly in the Z-axis here. But what we also get is the moment when the swimmer has sort of rolled over so that he's then swimming the right way. Those of you who are swimmers will know if you just do a tumble turn and then push off from the wall, you'll be facing upside down. So you need to roll over 180 degrees. And that's what this part of this y-axis is showing. Finally, we then come to the second length, where again we get those individual strokes. So there we have the breakdown of the swimming trial. This data can then be used by coaches, athletes, and researchers to help improve swimming technique. For example, by looking at the timings of the alternating strokes to optimize speed and efficiency in the water. So that brings us to the end of the presentation. So we haven't taken up too much of your time. Where we began by looking at what IMUs are, where we can find them, and how they can be used in sport. We then looked at how we can integrate them with Nexus, how we can use them as a standalone product, and we finished by looking at some technical questions about synchronization and global angles, as well as some user applications. So thank you for taking part. I hope you enjoyed it, and I think we're ready to take on some questions now.
Great, thanks, Nick. Yeah, we've got quite a few questions, but we have a good amount of time, so hopefully we can get to all of them. Just really quickly, on that swimming trial, was the sensor on the pelvis or somewhere else?
Yeah, that was on the posterior pelvis, sort of where you would place your PSIS markers if you know your plug and gate model.
Okay. So first question, if you are interested in higher rates for the global angle, is there a pipeline script to calculate that global angle from the other sensor data, or do you need to use your own script? And then second part of the question is,
unfortunately, the 225 hertz is the limit there. So if you wanted to get higher rates for global angles, that's something you'd have to try and calculate.
Okay, and then second part of that question is there any information available about the algorithm that Vicon uses to calculate the global angle?
No, I'm afraid we don't have any information to give out at this time.
Okay, so next question is, if you have 4 different sensors and want to capture global angles, do you have to do a separate calibration for each sensor, or do you calibrate them all at once?
That's a good question. You do need to calibrate each sensor individually in terms of taking it through this figure of 8 wand wave. However, if you're wanting to just align them with the Vicon global coordinate system, we also have the option to sort of copy that alignment from one sensor to the other. So you can just click that and it applies the like a rotation matrix onto your other sensors.
Okay, and then kind of a similar question. How would you calibrate the IMUs if you would want IMUs standalone, i.e. when there's no global Vicon coordinate system?
Yeah, so you would essentially be taking your sensors through a figure of 8 pattern, just without the active wand, attach the active wand. So I'm not sure if you can see my camera, if I've got one here, but you would just sort of take it through that sort of motion. Again, you do it for about 10 seconds, and then you just let the sensor self-calibrate, so you can keep it flat on the table or something like that.
Okay, great. So this next attendee has 2 questions. So the motivation of combining IMU with Vicon is a bit unclear to me. Is this for motion capture applications? And if so, why would you not use the optical markers?
Yeah, that's right. So if you were to use IMUs for things like calculating joint angles, so let's take the example we saw in the video of cricket bowling. If you wanted to know your flexion extension at the elbow purely from IMU data, you'd want to validate that with a trusted source. So in this case, the optical motion capture data calculated from the markers. So the other option is, or the other reason might be to include IMU data with your optical data. So I'm sure there are plenty of things that would find use for this, but one example could be if you wanted to look at how impacts occur, let's say in football headering or something like that. You could have a IMU sensor tracking your head acceleration, and then obviously the optical marker data that could be used for your biomechanics.
Great. And the second question from that attendee is, as far as I know, IMUs have a drift, which is more pronounced for position estimates. Is this somehow corrected in Vicon?
Well, the drift itself has, I mean, there's many sources of drift in IMU. So if we're talking about global angles here, it could be things from within your current environment. So it could be either magnetic objects, or it even could just be any sort of metal which sort of distort a magnetic field. Obviously, the global angles use the magnetometer as part of the calculation. So if you distort that, then you get some drift in your sensor. There will be some drift over time as well. So if you are looking at the synchronization of the sensors, let's say, if you're not using a Vicon beacon, and then they'll be susceptible to drift, something like 20 microseconds over an hour. I'd have to double check that, but it's not too much.
Okay, so another multi-part question from a different attendee. The first one is it possible to remove the segment alignment afterwards to get the position in the Vicon world frame, or is the only way to calculate this manually after exporting the segment pose?
Possible to remove the segment alignment to get position. Do you mean to get the position of the IMU in the global frame? I think that's sort of how I'm interpreting the question. So I think I would just use marker positions attached. So placing the IMU itself onto a marker in order to track its position would probably be the best way to do that. I'm not sure if that answers your question.
Just some more context from them. They aligned the IMUs with the Nexus calibration procedure. And she says, we did this for our recording, but later found out that this gives us the global angles relative to the tracked body segments instead of the global Vicon world system.
I see. So yeah, one of the options in Nexus is, rather than aligning your sensor with the wand, is to select a segment. So I'm guessing here that you chose this option rather than the wand option. I'm not entirely sure if there's a way to revert that. It's something I'll have to look into, I'm afraid.
Okay, and then you may or may not be able to answer this one. How is the global angle calculated if the segment is not available at a time due to missing markers? Will the global angle be adjusted accordingly if the cap motion has been post-processed and the position of the segment has shifted?
Okay, so the global angles that you get from the sensor are taken directly from the center itself. So it uses the accelerometer, magnetometer, and gyroscope to calculate those. So it's not actually dependent on any of the marker data. If you're looking at global angles in a tracked segment, then we have options to fill any missing data within our post-processing.
Okay, so next question is, he says, with other types of IMUs I've used in the past, I've used a reference movement, i.e. knee flexion, to align the IMU with the anatomical coordinate system. Vicon obviously doesn't use this as a reference movement since it uses the markers on anatomical landmarks. During validation, how do you make sure the two anatomical coordinate systems are equal? Is it necessary to use a reference movement for anatomical alignment to make it comparable with IMU anatomical coordinate system?
Well, I guess when you're looking at the global angles, it's just a case of taking the raw global angles that you've exported and then applying your offset. So let's say you've got your marker data, which you can then use to measure, say, two vectors from the hip to the knee, and then from the knee medially. So you can take those two vectors from your marker data to create a your segment or your optical motion capture segment, and then it's just a case of taking a rotation matrix from your segment onto your global angles that you've captured from your IMU. I believe that's the case. That's what you'd have to do there. You can obviously just use the IMUs in a way that you've used in the past. You can just export the raw data, and using those motions like the knee flexion extension or something like that, you can use that in exactly the same way to calculate your anatomical segments.
Okay, so next question, is there an aligned signals option with the Vicon Nexus to make sure marker force and IMU data are synchronized, or is that built-in option only for the Capture U to align IMUs?
Oh, I see. For when you export data, so when you open up your C3D file essentially, and you process your C3D, and you see your IMU data that you've already transferred, it's the same thing has happened. It's already aligned it with your Vicon system data, and all the sensors will be aligned in that way as well.
Okay, great. Is it possible to measure the step length with an inertial sensor?
It may very well be possible to do that. I'm sure it is. We don't have any built-in widgets or models that do that just yet. But you more than able to go and capture some data and do that yourselves.
Can you set the sampling frequency of multiple IMUs differently? I.e., could you have the majority set at 225 hertz to get the global angles, and then on a single one on the distal segment, get the high G accelerations, but not the global angle?
Yeah, that's right. The individual sensor components that you select are applied for each individual sensor. So it would just be a case of selecting that sensor and setting it to high G only.
Great. What is the max measurement duration for a single standalone measurement?
Well, the sensors themselves are sort of limited by their battery life at the moment, but I think you can get something like 8 hours of data onto the IMUs before they die. As it goes for the motion capture stuff, I guess it depends on how much space you have on your PC as well.
Okay, thanks, Nick. Is that affected by the sampling rate? Could you extend the battery if you have a lower sampling rate?
Yeah, that's right as well. If you, it depends on your capture frequency. So if you're using all components, then yeah, you'll take up space a bit quicker and also drain the battery faster.
Okay, great. I think that is all the questions. Let me just double check. Oh, yep, here we got a new one. Is the ability to align the IMUs with the global angles a unique component of these sensors? I've never heard of matching IMUs with the Vicon Global Coordinate System before.
Yeah, I guess it is. It's unique. I mean, these are the only sensors that we do inertly integrate with. But I'm sure if you did have some other types, there's some other ways of post-processing that to align sensors with the global coordinate system as well. But the way that we do it, it is unique to Vicon.
Yeah, I think the unique part is that they integrate pretty seamlessly because they're built by the same company.
Yeah, that's right.
Okay, so that is all the questions we'll take today. If we didn't get to them, I think I've asked all of them, but if we missed one somehow, we can follow up after. But Nick, thank you so much for that great presentation, and thank you everyone for joining in. Like I said, you will get the recording if you want to watch anything again. And then if you need to get in contact with either myself or Nick, you can just go through the support channels. So thanks again, and I hope everyone has a good holiday.